sampling distribution and central limit theorem. Previously, we learned to compute probabilities or proportion for a randomly selected sample individual from a normal distribution. In practice, statistical studies involve sampling several and perhaps many individuals. So for these cases, we should consider, let's look at this. Let X bar is the mean of a random sample size of size n, drawn from a population with a mean and standard deviation. Then the mean of a sampling distribution, the population mean, is same. Okay. So what we're doing here is that the sample we get from the population, the mean of that sample is equal to the population mean within normal distribution, within normal population. But standard deviation changes. The standard deviation of sampling distribution is sigma of sample distribution is population standard deviation divided by square root of n, square root of sample size. The standard deviation is sometimes called the standard error of the mean. So let's look at this example. Population has a mean of 25 and standard deviation of 6. Find the mean for the sampling distribution and standard deviation with a sample size of 25. Round your answers to one decimal if needed. So again, the mean from the sampling is equal to population mean, so it's 25. However, the standard deviation is different. Standard deviation changes where we do square root of n. Standard deviation is population standard deviation is 6, so we do 6 divided by square root of 25, which is 6 over 5 equals 1 over 2. So when we're sampling, we can use the same mean from the population, but we need to adjust the standard deviation value. Central limit theorem. For any population, if the sample size is large enough, which means we usually large enough as greater than 30, the sample mean will be approximately normally distributed. In this case, X bar has an approximate normal distribution, which means the mean is the population mean and standard deviation is the adjustment we just looked at. For normal population, the sample mean will be always normal for any sample size. So keep that in mind. So central limit theorem, essentially need to remember the large enough size, greater than 30, we have the sample mean is approximately normal distributed. If we're getting the sample from the normal population, then it will be, of course, always be normal for any size. So let's look at an example. A sample size of 5 will be drawn from a normal population with mean of 60 and standard deviation of 12. Is it appropriate to use the normal distribution to find the probability of X bar? Yes. Although size 5 is less than 30, the population is normal because the population is normal. So it is appropriate to use the normal distribution for the sample. But of course, for this, we have to find the mean and the standard deviation. Well, mean is same, 60, but standard deviation, we have to use the different value, which we'll do in the next part. But hypothetically, if this problem did not say that it's from a normal population, just from a population, then it's not appropriate because size is small. If it did not have this word normal, but then if size was, let's say, 40, then it is also appropriate. So it matters what we get sample from. If we get sample from the population, just any population that is not normal, it has to be greater than 30 to assume the normal distribution. If we're sampling from a normal population already, then we can already assume that sample is also normal. So find the probability that X bar will be between 50 and 70. So here we're using the same idea of z-score. So mean, well, new mean was actually same as the population mean, but standard deviation changes. It is the population standard deviation divided by sample size square root. So it'll be 12 over square root of 5, which is, because size n was 5 here, which is about 5.37. So that's the new standard deviation. So when we find the z-score, let me go to the formula. It's the same idea as this, but standard deviation value is different. So there's another score, another formula for this sample mean, where sample mean minus population mean divided by the adjusted standard deviation. So I already found this value for this problem to be 5.37. Okay. So to find the z-score, we can use this problem. So the important thing is when you read the problem, you need to be able to recognize when to use which z-score formula. Here is a sample, we're dealing with a sample within normal distribution. Therefore, we must use this formula to find z-score. So for z-score for this one, will be 50 minus population mean, which is 60, divided by new standard deviation, this value, or this one, 5.37. For this one, will be 70 minus 60 divided by same standard deviation. So find each of these values. I get negative 1.86. For this one, I get positive 1.86. So we're finding the probability. So we're finding the probability z such that between these values. So once you come this far, it is a similar to regular z-score probability problem. The main difference is that we have a new formula for the standard deviation. So this, we just find z less than 1.86 minus probability z less than negative 1.86. So from the z table, we subtract. This is the z value, a probability value I get from this 1.86 z-score. For this one, I get 0.0314. If I subtract, I get 0.9372. Okay, so let me kind of draw a boundary. So, what does this mean? Okay, in terms of interpretation, this means the probability of mean of those sample size 5 will be between 50 and 70 is 0.9372. So we're not selecting one individual on these problems. We're selecting 5. We're selecting 5 is drawn from the normal distribution. 5. That's why the standard deviation also is changing, because we're not selecting 1, we're selecting 5. So probability of mean of those randomly selected 5 being between 50 and 70 is 0.9372. Okay, if appropriate, it is appropriate, we can use normal distribution. Find the 80th percentile of X bar. This, again, similar to what we did before, is giving us the area left of 0.8. This area is 0.8. Find this z-score, and then find the X bar value. Right? So let's find the corresponding z-score. So from the z table, we're finding the area left is 0.8, about 0.8. So zero point 0.8 is this one. 0.7995 is closer to zero point 0.8 than 8023, right? So this one, corresponding z-score is 0.84. So this z-score is 0.84. Then we know that z-score is x bar minus the mean divided by standard deviation, which is new. We have to adjust it for this problem. We know all the other values. We know the z. We're looking for x bar in this problem. We're finding x bar. Oops. Minus the mean, which is 60, divided by we know the x bar. So we're finding the x bar value from the z-score we got here. We know the formula is x bar minus mu divided by new standard deviation formula. We know all these other values. We know this one, and this one. So let me write that here. 0.84 is the z-score. We're finding for x bar. Mu mean is the 60. This value I found earlier, 5.37. So solve for x bar. Multiply by 5.37 and add 60. Then you get x equals 6451. X bar. So this is the value they'll give us. The area left side is 0.80. So let me remind you, this was okay, very similar to we could use this formula. But the thing that will change is this standard deviation value. We have to adjust the standard deviation for these problems. So let's look at another similar example. A sample size of 42 will be drawn from a population with mean of 52 and standard deviation of 9. Is it appropriate? Yes. Yes, because 42 is greater than 30. So it is large enough. Large enough. So when I do this problem, I actually suggest find the mean, which is 52, but also calculate the standard deviation, which is 9 over square root of 42, which gives us about 1.39. So these are the mean and the standard deviation we work with to find the z-scores now for these problems. So for part B, find the probability that the sample mean will be between 53 and 54. So what we're finding is, in this problem, we're finding the probability that the mean value of 42 sample is between 53 and 54. So we find those two z-scores. Z-score for Z for 53 is 53 minus the mean, 52, divided by new standard deviation, 1.39, 1.39, which gives me 0.72. Z for 54 is 54 minus 52 divided by 1.39. Let me highlight this standard deviation value again because we cannot just use 9 here. We must use this one. Okay, so we found the two standard deviation values. So we're finding the probability between those two. So we're finding probability such that, oh, sorry, I wrote the same number again. This is not 1.39. Oh, sorry. Apologize. It is 1.39, same. I forgot to write the z-score for this one. So this is correct. This z-score is 1.44. So we found these two z-scores. We're finding probability such that z is between 0.72 and 1.44. So which is same thing as we're finding z less than 1.44 from the z table and subtract finding z less than 0.72. So find each of these from the z table, which you get 0.9251 minus 0.7642. Then you get 0.1609. So what does this mean? This means the probability of mean value, the average value of 42 samples being between 53 and 54 is 0.1609, which also we can say the proportion of mean value of 42 between 53 and 54 is 0.1609. Find the 45th percentile. If appropriate, it is appropriate, we can use the normal distribution. That's what they're asked. That's why they're putting if here. It is appropriate. Find the 45th percentile x bar. So that means we need to find this area for z-score. Well, area is given, excuse me. This area is 0.45. We need to find this z-score from the z table. So here again, area is given. Area is 0.45. So 0.45 is, oops, where's 0.45? It's right here, negative 0.13. Wait, is this closer? Let's see. This is 17. Oh yeah, so 3. Yeah, this is, yeah. Negative 0.13 is the corresponding z-score. Negative 0.13 is the corresponding z-score. So we want to find, so let's try to use this formula for this problem. Raw score. This is essentially a raw score problem. Again, we have to be careful with the standard deviation. We're finding x bar z times standard deviation plus the mean. But we have to be careful here. This is not the given standard deviation because we're doing sampling. It is 1.39. This one, we have to use this one right here. So z we found to be negative 1.3 times 1.39 plus the mean was 52. And if you calculate this, you get about 51.82. So this is the raw score such that will give us 45th percentile for this sample mean. So let's look at a problem within a context. The mean distance that the commuters in the United States travel each way to work is 16 miles. So that's the mean value. Assume that standard deviation is 8 miles. Okay, so that's the standard deviation. A sample of 75 commuters chosen. Okay. So although it's not given if the distance the commuters in US that data is normal or not, because 75 is greater than 30, we can assume that the sample mean is normal distribution. So let's look at the first problem. What is the probability? This is asking probability. That means that our answer should be probability in decimal between 0 and 1, not negative number either. And also, we need to find the z-score to find the area using the z table. What is a sample mean? What is the probability that a sample mean commute distance is greater than, another keyword, greater than 13 miles? Here, there are a few things we have to pay attention. Also, sample is 75 of them. So n is 75, which means what this problem is asking is what is the probability of that mean distance of those 75 commuters is greater than 30 miles. So we sample 35 commuters. What is the probability that the average commute distance of those 75 commuters is greater than 30 miles? That's what this problem is asking. So z, let's find the z-score. Because it's a sample mean 75, we have to use this formula to find the z-score. Well, x bar is 13. This, they're asking this. This is the x bar value, 13 minus the mean population mean, 16. Divide by standard deviation is 16. Divide by square root of 75. Now, let's organize this a little more. We have to be careful here. In this formula, x bar is this value. Let me use a different color actually. The x bar is the value we want to find greater or less than. I'm talking about from this formula right here. And this mu is the population mean that is given in the problem. The population mean is given as this right here. This right here. Okay, so don't confuse those means. And the order does matter. If you did 16 minus 13, our answer will be incorrect. Okay. So then, of course, we all have a adjusted standard deviation. We cannot just use 16 because we're not finding the probability of a one commuter. If we were to find the probability of one commuter, distance greater than 13, then it will be just 16 as standard deviation, if this is normally distributed, of course. Okay, so keep that in mind. Then we find the z-score. Once we find the z-score, the way we solve the problem is similar to the previous problems. So this z-score is negative 3.26. So what we want to find is probability of z greater than negative 3.26, which is 1 minus probability z less than negative 3.26. Because we cannot find the greater value directly, we have to find from the left side, and 1 minus to find the right side. So this value, let's find the z table, negative 3.26. Negative 3.26, 0006, very small number, 0006. So it'll be 1 minus 0006. It means the answer is 0.9994. So the probability that the mean distance of 75 kilometers being between, greater than 13 miles is 0.9994. Second question. What is the probability that the sample mean distance to be greater than 90 miles? So I would like you to pause the video and try this on your own. It's very similar to what we just did. Pause video, and when you're done, I'll go over it. So pause the video now. Okay, so let me go over this. First, we find the z-score will be x bar minus population mean divided by distance deviation. Well, x bar now this is the x bar value, 19, minus population mean of 16, divided by standard deviation, 8. Oh, I'm sorry, I think I wrote 16 here, but I meant to write 8. The number is still correct. I just wrote an incorrect number. This is 8. 8 divided by square root of n is 75. And if I calculate that, I get 3.26, positive 3.26. Since it is greater, we have to do 1 minus. So we're finding probability of z greater than 3.26, which is 1 minus probability z less than 3.26. And I can find this value from the z table, which I get 0.9994. This is 0.994. So then answer is 0.0006. So the probability that the mean distance of those 75 commuters greater than 19 miles is 0.0006. Okay, so let's look at part C. What is the probability for an individual to have a commute distance greater than 19 miles? Right, so let's assume normal distribution for now. This is one individual, not mean. Then in this formula, we're using this z-score, this one. We're not using the adjusted standard deviation. That's very important. That's why it's important to pay attention when we read a problem. We're selecting one individual. What is the probability that one individual I randomly select has a commute distance greater than 90 miles? Also greater. We also have to pay attention to that wording as well. Greater. So let's find the z-score. Z-score is x, in this case x, because not sample mean anymore, just one value, minus the mean, divided by standard deviation. X here is 19 minus population mean 16, divided by standard deviation 8, which gives us about 0.38. So I'm finding probability of z greater than 0.38, which is 1 minus probability z less than 0.38. So that is 1 minus, find this value from the z table, which I get 0.6480. Then that I get 0.352. So this is the probability of one individual having a distance, commute distance greater than 90 miles. So for these problems, we have to pay attention to the wording. If we're sampling, right, we're sampling them. Let's look at it right here. Sampling 75, sample mean 75. In that case, we're not finding the probability of one person, we're finding probability of 75 people. But we're looking, when we're sampling, we're looking at mean value of those 75. What's the average, arithmetic average? What's the probability that average commute distance of those 75 people being less than certain value, greater than a certain value, or in between certain values? So it's very similar to the probability value we've been doing, but main difference is we have to use this formula for z-score. And when we use this formula, the main difference is this right here. The standard deviation value must be adjusted according to this sample size n.